Hey everyone, welcome back to our channel. Today we'll be talking about caching. So what is caching? Caching is a technique used to store frequently accessed data in a temporary storage space so that it can be retrieved much faster when needed. Instead of fetching the data from its original source every time, which can be slow and resource intensive, caching keeps a copy handy for quick access. Think about when you visit a website. The first time it might take a few seconds to load, but if you refresh the page, it loads almost instantly. That's because your browser has cached some of the website's data to make it load faster. Cache is just not limited to web browser. It's widely used in both hardware and software. In this video, we'll be talking about CPU caching. Your computer's processor has something called a CPU cache, a super fast memory storage that stores recently used instruction and data instead of fetching everything from the slower main memory RAM. The CPU checks the cache first. This drastically speeds up processing time. So why should we care about caching? Caching reduces latency, saves bandwidth, it lowers the computational loads and hence improving performance. You can think about caching like the speed dial on your phone. Instead of typing in the full number every time you call a friend, you just press one button, instantly connecting you. Similarly, caching stores frequently used data for instant retrieval. Now we'll talk why do we need caching. So understanding why do we need caching, we first need to know what without caching. Without caching, the main issue is that accessing data from primary storage, whether it's RAM or disk, can be slow. Every time your CPU needs data, it have to fetch it from main memory, which takes time. Retrieving data from cache takes nanoseconds, from RAM takes microseconds, and from disk takes milliseconds. That's a huge difference in the computing terms. Another issue is repetitive computation. Imagine your computer recalculating the same thing over and over again. That's waste of CPU power. The same applies to network bandwidth. Websites, for example, often download the same image and scripts every time you visit, which wastes bandwidth. Caching solves this by storing frequently used data for quick access. Caching provides a solution by keeping a copy of frequently used data in a fast access storage area. Instead of fetching it from the slower main storage, the system first checks the cache. If the data is there, it's retrieved instantly. This greatly reduces latency, saves CPU cycles, and minimizes network traffic, making systems much more efficient. You can think of caching like you go to the library every time you needed a dictionary. That would be time consuming. Instead, you keep a dictionary at home so you can quickly reference it whenever needed. That's exactly how caching works, storing frequently your data for instant access. Did you know the first cache memory was introduced way back in 1968 in the IBM System 360 Model 85? Since then, caching has evolved to become a critical part of modern computing. Now we'll talk about CPU cache. But before we jump into details, what exactly is a CPU cache? Think of it as a small super-fast memory that stores frequently used instructions and data. Instead of accessing slower RAM and CPU checks the cache first. If the data is there, it retrieves it instantly. This reduces delays and boosts performance dramatically. Caches are organized into different labels L1, L2, and L3, each with its own role in speeding up your computer. First, we'll start with L1 cache. The smallest but fastest type of cache, it's built directly into the CPU core and stores the most frequently accessed instruction and data because it's so close to the processing unit. It provides the fastest access time. Think of it like the species in your kitchen, always within arm's reach, so you can quickly grab them while cooking. Next, we have L2 cache. It's larger than L1 but slightly slower. Unlike L1, which is specific to the single CPU core, L2 is sometimes shared between multiple cores depending on the processor design. Continuing our kitchen analogy, L2 cache is like your pots and pans stored in a cupboard nearby, not as fast to grab as species, but still easy to access when needed. Finally, we have L3 cache, the largest and slowest of the three, but is still much faster than them. It's shared across all CPU cores, helping with overall performance and efficiency, especially for multi-core processing. In our kitchen analogy, L3 cache is like our pantry. It holds bulk ingredients that you don't need immediately, but is still much closer than having to go to the grocery store, which is our RAM. The modern CPUs can have over 100 MB of cache memory. That's larger than some of the earliest hard drives. This massive cache size helps modern processors handle complex tasks faster than ever before. So that's all for today. Thank you for watching.